So that's our two news items. We'll suspend all other news because, quick drum roll here, James Webb Space Telescope is on the docket. Take it away, Jen.
That's right. So we've all at this point heard about the James Webb Space Telescope, but I don't know if most of us fully understand why this is such a big deal and why all these scientists around the world are so excited to have yet another space telescope up in space. I mean, of course, they don't have to worry about the atmosphere in the way, but there's already so many up there, including Hubble. And the other thing you keep hearing is that the James Webb Space Telescope is so much better than Hubble. Better than Hubble? What does that even mean? What could possibly be better than Hubble? Well, lucky for you guys today, I'm here to let you know about what all the excitement's about, because in fact, James Webb is extremely exciting and there's going to be so much happening. So before I actually start, I'm going to tell you a little bit about James Webb, which was actually formerly known as the Next Generation Space Telescope, a very fitting name. And they ended up renaming it based on a gentleman who worked for NASA, I believe in 2009. Don't quote me on that date. So this is actually an infrared space observatory. It's going to be sent up there to explore the history of our entire universe. This will look at solar systems, including our very own. We actually haven't been able to answer all our questions yet, so yes, we do still need another telescope to do that. And it'll be doing a lot of great work out there. Now, this was actually put together by an international collaboration, and it will actually complement the work that's done by the Hubble Space Telescope. And as we know, the Hubble Space Telescope has led many, many scientific breakthroughs. So to be able to kind of complement it already kind of sets you off knowing there's going to be many scientific breakthroughs just coming from Webb on its own. Now, I said international collaboration because it's a collaboration between NASA, the European Space Agency, and the Canadian Space Agency. I definitely want to plug that in since it was Canada Astronomy Night in Canada. I like it when the European Space or the Canadian Space Agency is part of all these different things. But so what's different between Hubble and the James Webb? They're both space telescopes, right? Well, for starters, the James Webb actually has a larger primary mirror, which is 6.5 meters in diameter, versus Hubble's, which is only 2.4 meters.
Only,
and that's just
she says, only. I mean, really, only.
compared to 6.5.
Okay, fair enough. But 2.4 in orbit, I mean, wow. All right, anyway, sorry, go on. Yep.
We'll come back to that, Professor. And
I dare say we will.
One more time. But with this larger diameter for James Webb, it will actually allow it to collect more light, because it's kind of like a telescope's like a bucket of water. The larger the diameter, the larger the bucket, the more water, therefore the more light. In analogy. So the more light basically also means we're looking further back in space. And Webb's primary goal in this entire thing is basically to look as far back into the universe as possible. And to do that, it needs to be very sensitive to faint infrared signals. So that's another difference between Hubble and the James Webb. It's the coverage of wavelengths. So for James Webb, it's between 0.6 to 28.5 microns, whereas Hubble is 0.12 to 17 microns. And that actually isn't at the same time. They ended up having to modify, and now it's a smaller range. But between that, there's also one more difference, which is their orbit. Both observatories are going to be in completely different orbits. The James Webb will actually be put into orbit at a point called the second Lagrange point, L2. And at this point in space, the telescope would be able to orbit the sun, but keep a distance of 1.5 million kilometers away from Earth. And by doing that, it's going to be in a configuration where it's always in the same place with respect to the sun and the Earth. So the sun and the Earth will always be on a specific side of the telescope. So there's actually 5 points where this is possible, where this configuration is stable. And this is basically a 3-body problem where 3 bodies could orbit each other and they can stay in the same position relative to each other at the same time. This is actually thanks to an 18th century mathematician who found the solution to this 3-body problem, and it turns out that there are 5 solutions. And this specific telescope will be at the point number 2. And it'll actually allow the telescope's large sun shield, which I'm going to get into in a little bit, to protect the telescope from the light and heat of the sun, the Earth, and the moon. So anything the moon or the Earth might reflect. Whereas Hubble, on the other hand, its orbit is actually around Earth. It's not around the sun. And its distance is actually a lot closer than the Earth-Moon distance. So again, two completely different situations for Hubble and James Webb. But why is this important? Why is the orbit of James Webb so important? So the telescope itself will actually be it'll be operating in negative 225 degrees Celsius. So that's really cold temperatures. But the thing is that on one side of the telescope, it's going to be extremely hot, whereas on the other side, it will be extremely cold, almost to the point that you can boil water on one side, but you can freeze nitrogen on the cold side, which is kind of crazy. But this is super important for the James Webb, mainly because of its primary observations will be in infrared, which can sometimes be felt as heat. And because the telescope will be observing these very faint infrared signals of these very faint objects that are very, very far away, it will need to shield any extra noise that might actually affect the data. And that noise would be anything that's bright or a hot source. And that actually includes the satellite itself, which I thought was kind of neat. So I mentioned that it's colder on one side and hotter on the other. The colder side goes up to negative 233 degrees, which is the side that has the science instrumentation, the detectors, the filters, the mirror. And then the hotter side has the solar panels, the communication antenna, the computer, and the steering, which basically has the wheels and the jets on that side as well. So, I mean, as any scientist or any observational astronomer knows, the first thing you do is when you go up to the dome is you cool the CCD. And you have to cool it quite a bit. The colder, the better, as a matter of fact, for your data. So in this specific situation, it's really, really important that the cold side stays as cold as it does, even though you have a computer and things like jets that might be heating up on the opposite side. So the sun shield kind of plays a huge role in this entire spacecraft design. And for it to actually be effective in protecting the other side, kind of acting like a sunblock, it needs to make sure that it's protecting it from the light and heat from the sun, moon, and Earth, which by being in the second Lagrange point allows them all to be on the same side of the telescope, which makes things a lot easier for it. In fact, there's actually other satellites that are at this exact same point where the James Webb will be. Those are telescopes such as WMAP, Herschel, and Planck. So there's obviously something very significant about this very specific point. Now, at this orbit, it will take the James Webb Telescope about 6 months to complete one full orbit. But the good thing about this is that it will always be out of the shadows of both the Moon and the Earth, unlike Hubble, which actually goes in and out of the shadows of Earth every 90 minutes. So James Webb is certainly lucky in that way. It gets uninterrupted science observations 24 hours, 7 days a week, which is great. And it also makes it a little easier to communicate with the observatory because you have constant communication, so you can download data and send commands as needed. But other than that, which are also really great reasons, what exactly makes the James Webb so great? Well, there's three simple words. Maybe not so simple, but there's three main things. There's innovations, there's instrumentation, and there is science. So the James Webb Space Telescope will be, or is believed to be, the leading observatory of the next decade. And it will do things like study every phase in the history of our universe, ranging from the first luminous glow after the Big Bang to the formation of the solar systems that are capable of supporting life on planets just like our very own. It will even study the evolution of our very own galaxy, of our very own solar system. Well, in order to do this kind of science, we needed to make some innovative breakthroughs in technology. And that's exactly actually what the engineering team of James Webb did. This actually includes making the primary mirror, which is 6.5 meters. It's made up of 18 separate segments, and they actually unfold and adjust into the shape they need to be not right after launch, but once it deploys. And of course, when you want to launch anything, you always have to worry about your payload. You want it to be as light as possible. So in this case, they actually made these mirrors out of ultra lightweight beryllium. So they've certainly thought of it all. The major innovations that are going to be on board is the lightweight optics, the deployable sun shield, the folding segments of the mirrors, improved detectors, the cryogenic controls for the mirrors, and micro shutters. But the most important between all that is the Webb's big. It's basically the size of a tennis court. It's 5 layers, and it's the sun shield. And the reason this is such a big deal is because it actually reduces the heat from the sun more than 1,000,000 times. So it's things like this that will pretty much, I think, make it possible for us to do things like human missions to Mars, because we keep making these adjustments in our technology today. And of course, on board are the instrumentations. There are 4 instrumentations, cameras and spectrometers, all of which with detectors that are able to record extremely faint signals. So again, that's really important. All 4 of these components are in something called the integrated instrument module on the James Webb, and it includes things like the mid-infrared instrument, which has the cryocooler for cooling the mid-infrared detector to a very cold 7 Kelvin, which is negative 266 degrees, 0.15 degrees Celsius. It also has the near-infrared spectrograph, which has the programmable micro shutters, allowing the specific spectrograph to actually observe up to 100 objects simultaneously. And then it also has the near-infrared camera and the fine guide sensor with a near-infrared imager. Now, I keep using this word infrared, and unless you are an astronomer in a very specific field, you don't quite really see what you can get out of infrared in comparison to X-ray, for example. So why is the Webb optimizing its equipment for near and mid-infrared light? Well, again, it always comes back to the primary goal. The primary goal of Webb will be to study these galaxies, these stars and planets that formed in the early universe. And these very first stars and galaxies in the early universe, for us to actually find them, we need to look really, really deep into space, and which means we also need to look really, really far back in time. Now, we know that light takes time to travel to us, and the further out we look, the further back in time we see. It's one of the golden treasures. But the universe is expanding. Alex actually mentioned that a little bit earlier. So the further out we look, the faster these objects are actually moving away. And in fact, the further back you look, the faster those objects are moving than the ones even closer to you. So it's not just expanding, it's expanding at an accelerated rate. And what happens to that light, it gets redshifted. So what that basically means is that the light that is emitted, for example, in ultraviolet or visible light, it gets shifted more and more into the red wavelength. So for very high redshifts, it actually gets shifted right into the near and mid-infrared part of the spectrum. And because we're looking so far back, in our case, it would be very, very, very high redshifts. So to study these early star formations in the universe, this very specific telescope does need to observe in infrared light. But it's also studying planets, planet formations in our local universe that aren't as redshifted as these far objects. So why would it need these infrared lights for that? Well, it turns out that these little baby stars and planets are pretty much embedded in the centers of these dense, dusty clouds hidden from our eyes in the visible wavelength. So, of course, an infrared optimized telescope would actually allow us to see through these dusts and clouds and into the birthplaces of these stars and planets, helping us answer so many questions. I'm going to briefly just point out the 4 main research goals, mission goals. I will go into the science of it if I have a little bit of time at the end, but I'm just going to go through those really quickly and then almost wrap it up. So there's four main mission goals. So there's the research for the first galaxies or luminous objects formed after the Big Bang. There's determining how galaxies evolve from their formation until now. There's observing the formation of stars from the first stages to the formation of planetary systems. And there's measuring the physical and chemical properties of planetary systems, including our own solar system, and investigating the potentials for life, both in our own solar system and the solar systems further out. Now, a lot of this does have to do with us looking back in space. So how far back can the James Webb really look? Again, one of the main goals, we want to see the first set of stars. And it's actually believed that these happen somewhere between the redshift of 15 and 30. Don't worry, redshift of 15 and 30 doesn't mean much to me either. All I know is those are high redshifts. And as I mentioned earlier, high redshifts just means that the object is moving away fast, further away, which means you're looking back into space and time pretty far. So at these redshifts, the universe was only about 1 to 2% of its current age. Its current age is pretty old. It's 13.7 billion years. But at that redshift, it was about 100 to 200 million years after the Big Bang. So that means if we start observing those stars, we're basically getting light from galaxies that have traveled for about 13.5 billion years over the distance of 13.5 billion light years. So for the Webb to be actually designed to discover and study these first galaxies and stars that have been formed in the early universe, it needs to be able to see these faint objects, which means it must be able to detect things that are 10 billion times fainter than the faintest star visible without a telescope. That I wasn't surprised about hearing. But it also means that it needs to be 10 to 100 times fainter than what Hubble can see. So there's another difference between Hubble and James Webb. James Webb will actually be able to see faint objects that are 10 to 100 times fainter than the Hubble could, which is a big deal. But there's one more telescope that I kind of wanted to plug into here, which was Herschel. The reason I want to bring up Herschel is because Herschel's also at the L2 point where James Webb will be, and it is also an infrared telescope up in space. So that's pretty cool. What's different about them then? Well, the main thing is obviously their wavelengths. It goes from, well, we know that Webb goes from 0.6 to 28.5 microns. As for Herschel, it goes from 60 to 500. And usually these are based on what their sciences are. So for Herschel, it's to look at these extremes, these most active star-forming galaxies, and they usually emit energy in the far infrared, whereas Webb is looking for early galaxies in the early universe, and that's usually emitted in sensitive IR. And of course, the difference of their diameter of the primary mirror. The Webb was 6.5, Herschel was 3.5, and Hubble 2.4 meters. I will not use the word only this time.
Very good, but you have only 3 minutes remaining.
Yes, so I'm not going to go into the science, even though the science is really cool. I will mention that after the Cassini mission, the James Webb will play a large role in planetary science because there are no other missions out there at the moment. But separate from that, just like Hubble, we're going to be able to have access to all of the beautiful imagery. In fact, the social media team that runs the outreach program for Hubble will actually take over the outreach for James Webb. And one last thing, of course, don't hold your breath just yet, because it will launch in October of 2018, and it won't start collecting data till 6 months after that. But the good news is it's planned for a 10-year mission, so definitely stay tuned.
Whichever way you want to cut it, and you sum that up very, very well. I mean, 20 years worth of chatting about James Webb is really what you've just summarized in 15 minutes. So that was a good effort. It really has the potential to unlocking so many of the questions which Hubble, in a very real sense, has posed. We always thought that Hubble would answer so many of the important questions of the day, astronomically speaking, where the day was late 1980s, early 1990s. And Hubble has been called the discovery machine. But as it has probed ever deeper, and who could forget the Hubble Ultra Deep Field and so on, we've realized that for every question it's answered, it's asked probably half a dozen more. And hence it has really set the stage for the James Webb Telescope. It's a technological marvel. Some people might say a monster, because of course it's like 6 years behind schedule and has run over budget by an amount that we cannot possibly even say on air. But the potential that the James Webb Telescope has is truly amazing. So it is exciting times ahead for everybody in the astronomical community, the public as well as the scientific community alike.
Absolutely, it's going to be very exciting.
Yes, well, you will be in a front row seat to see it. As you said, 2018, probably operational if all goes well and fingers crossed, 2019. And that's, I guess, one other little thing we should underscore just to finish this off. Unlike the Hubble, where there were servicing missions that were able to reach it easily, at this point in time, there is no capability to reach the James Webb Telescope if something goes wrong. Let's all hope that the Space Transportation System, the new space launch system from NASA, not to mention Dragon and SpaceX, they'll close that gap and we'll have the ability to reach James Webb if we need to. But fingers crossed it all goes well and that it is the first of 10 years for an extended mission starting in 2019. Thank you very much, Jen. So, folks, you've been listening to York Universe, the weekly broadcast of astronomy and astrophysics out of the York University Astronomical Observatory. No, we cannot tell the time in daylight saving time because it is 10 after the hour, but we had lots to talk about. We will be back next week to bring you all the exciting news, so please do stay tuned for that. With a bit of luck, it'll be clear skies at that point in time. It's Astronomy Night in Canada. Stay tuned for Western Worlds, Quirks and Quarks, Science for the People. From me, good night.
Good night.